I'm the newest member of RU Cool as far as faculty go, but I've been at Rutgers for about 10 years. So I started as a graduate student in Scott, and I've been working in this region on hurricanes and the coastal ocean for a while now. That being said, there's a lot of expertise in this room, and I really want to highlight that. I'm going to be doing a really high-level discussion of the cold pool, but if you have any questions about the cold pool, some of the best people to ask in the world are sitting in this room. For the long-term view of the cold pool, how we sampled it, how we sampled in the past, and how we sample today, Wendell Brown and Bill Boycourt are here. They have a wealth of knowledge. They've been working on this longer than I've been alive, so really tap them as much as you can. John Wilkins here, he's at Rutgers. He's been working on the Mid-Atlantic oceanography, coastal processes, freshwater input, tides, modeling, everything you can think of for a very long time. We have Josh go ahead and introduce himself, who works on physics and fish and physical ocean processes in the region. You're going to hear from Scott. We have Rich Dunk, who's been working on sea breeze and its interaction with the cold pool for, again, longer than I've been alive. So there's a real wealth of resources in this room in the Atlantic community. But there's another subset of scientists in the room, and that's the fishing community. They've been touching the cold pool, touching the ocean for decades and decades. So we want to tap that knowledge as much as possible. I'm going to do this high-level overview, but I probably know the least about the cold pool compared to those people in the room. So really, the discussion is going to be very important. So moving forward. My job is to set the stage a little bit. So I'm going to go through some background on the circulation in the Mid-Atlantic Bight, talk about the vertical structure of the cold pool, its spatial extent, how it forms, how it breaks down, and then a slide on how it's changing. So I'm not going to go too far into climate. If you have climate questions, we also have Vince Saba in the room, who knows more about the regional climate trends and can speak to that on one of the panels in the afternoon. So, and then after that, I'm going to pass it off to Scott to talk about some of the processes between the ocean and the atmosphere. All right. So, to get started, this is the Mid-Atlantic Bight. We're all sitting here in New Jersey, in Tuckerton, right kind of at the center at this crux. It extends from Cape Hatteras to Cape Cod, about 1,000 kilometers. We have 10 states. We have the largest population density in the U.S. New Jersey actually has the largest density in the U.S. So lots of people, lots of commerce, lots of different things going on. Some notable physical features. We have large bays and sounds. We have this very wide continental shelf, shallow, gently sloping continental shelf. There's these canyons at the shelf break, so that potentially allow for processes to transfer water between the continental shelf and the deep ocean. There's shoals up here where you can have large tides and a lot of mixing. There's a Hudson Shelf Valley that kind of splits the New York Bight into the north and south. And then we have these ridge and swale topography that can drive somebody up along the coast. So these are some of the notable features throughout the region, and you might hear some more about these throughout the day. But before we get too much into this the local oceanography, I want to zoom way out. So if you open a textbook and you look at what the ocean circulation looks like, this is kind of the first thing that you might come across. This is what a lot of us probably came across early on in school. And this is really a schematic of what's going on in the ocean. So basically we have these gyres in our different ocean basins. We have warm water coming from the tropics to the north, and then we have cold water coming back to the south. Really simple, right? Just a big garbage patch here, maybe a smaller one here, everything's hunky-dory. Well, that's not really what it looks like. This is what our large-scale ocean looks like. It gets very complicated very fast. So here, this is the Gulf Stream. This is winds overlaid on it. Gulf Stream will come back. We have Gulf Stream transporting that heat to the north. But once it gets past North Carolina, it gets really wavy. You have all these eddies, these small-scale features that can impinge onto the shelf. So it gets very complicated in this region, and there's a lot of potential interaction at the shelf break. There's also this cold water that can come down from the north and interact along this area. So we have our cold polar water at the north, and we have our warm tropical water in the south, and they meet right here at our home in the Mid-Atlantic Bight. So this cold water, this is another schematic, but it's a zoomed in one, with a little more detail. So here you have the Gulf Stream going off to the north and east, making these big bends. These change depending on instability. You can have some waviness to this. You can have eddies spin off. Transports all that warm water north. Then you have Greenland. You have the Labrador Sea. This is cold water. You get these Labrador coastal currents that can come south along the along the shelf break, all the way past Canada and Newfoundland, Grand Banks, into the Gulf of Maine, and all the way down into the Mid-Atlantic Bight, where it meets up with the Gulf Stream right here, and you get some recirculation. So we're in this really interesting area where you have your tropics and you have your polar oceans meeting. That means we're influenced by a lot of remote processes. A lot of things that might change up here or down here in the tropics can affect our oceanography, can affect our stratification, affect the environment and our fisheries. This is a really important thing to keep in mind. So as we zoom in a little bit more, so we're back to our Mid-Atlantic region. So here's Cape Hatteras, here's Cape Cod. This is a schematic of that coastal current. So you can get that cold water coming in from the north. On average, this is about 5 centimeters per second. The average generally never happens. There's a lot of variability. But on average, you get this slow-moving coastal current bringing cold water to the south, making our continental shelf cool. And then this boundary current, Gulf Stream, moving to the north. We also have a lot of freshwater inputs, so coming from places like Hudson River, Hudson Bay, Delaware Bay, Chesapeake Bay, Long Island Sound, as well as many other smaller rivers throughout the region. Scott's going to talk a little bit about some of that freshwater input, and he's also going to talk about how some of these salty eddy fronts and meanders, how they interact with the shelf break and can influence our shelf. And then lastly, there's a few things that don't make it onto this plot, but we have a lot of tidal mixing. We have a lot of variability in tidal mixing. So we might have high tidal mixing here over off of Nantucket. We have a lot of air-sea interactions. We have a lot of storms that come through. We get storms. We get a twofer. We get our winter storms that come through in winter, spring, fall time frames. And then we also get our tropical cyclones, as we all know, that can come through. So no matter what season, we're usually getting hit by some sort of storm. There's a lot of radiative heat flux, so heating from the sun, and then those shelf break canyons, as well as other processes that I mentioned earlier. So I'm mainly giving you this surface view, but we're all here to talk about the cold pool. What does it look like underneath the surface? One of the first papers to look at one of the first publications that looked at profiles in the water column in the Mid-Atlantic Bight was this paper by Henry Bigelow in 1933. So the cold pool is not a new feature. It's not a new feature to study. We've been studying it for almost 100 years. There's a wealth of knowledge about this out there, and so hopefully we can bring some of that to bear today. These are 3 cross-shelf transects of temperature. They were compiled from lots of ships of opportunity, commercial ships of opportunity. There's a long history of commercial ships collecting data throughout this region, but also from these historic light ships that were out there guiding traffic, but also working on weather, doing science, and studying the ocean. This is the lightship Sandy Hook, which was eventually replaced by Ambrose Light. So if you ever see Ambrose Light referenced, that's where the name came from, is one of these light ships. There's a Nantucket, and I think that's actually parked somewhere, maybe in South Street Seaport in New York. There's one park. I don't know if that's Ambrose or Nantucket. So you can go see one of these in New York if you wanted to. But there's been a lot of data. This is cross sections from June. This is off of Nantucket, Martha's Vineyard area coming south. Then we have the New York Bight section B, and then C off of Delaware Bay. We just look at one of these. I'm going to pick this one, my favorite, in the central New York Bight. What you see is our temperature structure. So this is in June. You have some warmish, getting warm surface temperatures, so 14 degrees Celsius. This is depth here and distance offshore here. And then once you get to about 20 meters, you see this very, very sharp change in temperature. You go from 14 degrees to 13 degrees, all of a sudden to 7. So you get about a 7-degree C change in about 5 meters. This is one of the most rapid changes in stratification in the world that you get in the Mid-Atlantic Bight. And this is it being set up here. So all these isotherms here, lines of constant temperature going offshore. And what you start to see is this little feature, this little bulge feature here. You see it here as well, this 9 degrees C, 10 degrees Celsius feature. And that is some of the first depictions of the cold. So this was 1933. In 1982, there was a paper by Houghton et al. From Lamont Doherty, Geological Observatory at the time, now Earth Observatory, and that's Columbia. And this was one of the first publications really talking about the cold pool, defining it, talking about its evolution. So here are maps, and these are collected, these are from the MARMAP program, which is actually Northeast Fisheries Science Center, collected these data for years and still does. This data is still collected by NOAA to this day. And so in a different flavor, but still the same idea. Going out the ship, putting a temperature probe in the water, salinity probe, and putting it on a map. And so here, this is in spring, winter moving into spring. You can see this 10 degrees C line here, and then it's colder inshore. It's probably hard to see, but this is like 4 degrees C, 2 degrees C. So this is wintertime water. And then this is sort of this feature starting to form. This is in May. And then as we warm in our shallow water, we actually get this 10 degrees C line that starts to form on the inshore side, and you get what looks like this pool feature, this cold pool feature. It's attached to the north here, so it goes all the way around, and there's some connection to the Gulf of Maine, and then it goes offshore right here. And then in August, we see it actually get cut off and isolated from the north, and so you have this pool feature that's kind of left here on its own. And then September, it disappears. So generally, our cold pool exists kind of between May to September. There's quite a lot of variability there that we'll talk about. In some later papers, this is more formally defined, but basically we're looking at waters colder than 10 degrees Celsius and salinity less than 34 psi. So that means it's not this water that's further offshore. It's really focused on this shelf water. Okay. So we keep jumping forward in time. So these are papers. This is from 2017 from Steve Lentz. And then I also put on some cross sections from some of our autonomous underwater gliders that we put out off Tuckerton right here out to the shelf break. So these are composite maps of bottom temperature, and these are composite maps of slices of temperature through the water column right through this center area. And over here, this is near bottom temperature, average kind of for the whole region. And then this is time, so January, February, March, all the way into December. And so if we step through this again, we get this spatial view. You can see this cold water feature in May. You can see it kind of starting to form into this cold pool. And when we look at it vertically, we see this cold bottom here, but we start to see warmer surface temperatures right at about 10 degrees Celsius. So this is that green here is, I don't have a color map for that one here, but basically that green is your slightly warmer water. We're getting up to 15 degrees C in June, and you can see this really well-defined cold pool feature here, and some more definition here, but we're still connected to the north. So in May, so basically what we have is we have cooling in winter from the atmosphere, as well as transport southward of that cold Labrador Sea, Gulf of Maine water into the Mid-Atlantic Bight. We have that continued cooling into February, March timeframe, and then eventually you get this rapid warming that essentially caps off that cold pool. You don't get any air-sea heat flux into this cold layer. It basically is all trapped in the surface layer. And so once that happens, start moving forward, once you get it isolated from the surface, we start getting this gradual warming, mostly through tidal mixing and a few storms that might come through, of about 1 degree C per month. So this very slow, very gradual warming in the cold layer, but very rapid warming in the surface layer. In July and August, you can get up to 28 degrees Celsius. So we have 28 or higher, 28 degrees Celsius in the surface, maybe 10 degrees C in the bottom. So this thermocline can be anywhere from about 15 degrees Celsius through that interface, a very large temperature difference and one of the largest temperature differences in the world, like I mentioned earlier. So July, August is kind of our peak cold pool season. We're warming up a little bit. And then September, October, you start to see it deepen. You see it lose some of that cold water mass, still maintain its shape, but lose some of that cold core water. And then here starts to get cut off in October from the north. So our evolution of the cold pool is we have that cold water coming from the north, we have the remnant water left over, it gets capped off, but what starts to break it down? Some of it is tidal mixing in this region, but really the big thing that starts to break it down is from storms. So depending on when storms come through, that's when our cold pool is either going to get shut down or keep going. So there's a lot of variability in that time. So this crash right here is from storm events. If we want to look at that in detail, I won't get on this too much, but this is another paper by Steve Lenz, and it shows that cold pool temperature. You get these very rapid drops and changes in temperature lined up with wind stress, and this is in August and September. Your surface heat flux is relatively constant throughout this time frame up until about October, November, and so it's really these big storm events that makes that water column. All right. I don't know if this is going to work. So just to wrap all that up, if people are having problems visualizing it, this is a movie of the, it's actually the 12 degree C isotherm, but it's a movie of the cold pool throughout the summer. This is generated from one of the modeling products that John Wilkin has worked on for years. It's been funded by Marcus. This is from one of the older models, Espresso. But you can see that feature moving around, changing, and then starting to shrink slowly in time. I'll play it one more time. Okay, I'm going to move on for the sake of time. Again, I mentioned I'm not a super expert in this, but there are people in the room to talk to. On this, in general, so how things are changing with climate, in general, what you can see, this is 1975 to 2015. In general, through all seasons from this particular paper, which is from observations on the shelf from the MV Oleander that goes between Bermuda and New Jersey, in general, you see a warming trend. This is shelf depth average. It's not specific to the cold pool. And so there is a warming trend annually, but also across seasons. There's a lot of different studies beyond this one that have talked about what those rates are, whether we're warming rapidly or slowly, and where we're going to go into the future. I'm not going to get into that here, but there is a general consensus that we are warming. The questions are about how fast. And this is kind of, if you look from 1977 to 2013, annually we're warming by it's about 1/4 degree per decade. If you look at just these shorter time periods, depending on where you pick to start your line, you can get some different rates of 0.1 degrees C per year, or 1/4 degree per year. There's other studies that have kind of tried to revise this, so I wouldn't really take this too seriously yet. But it is something we definitely have to consider, and general trends are warming. So I just want to put that out there as a topic for discussion later on. When it comes to why we're warming, there's a lot of research going on that, but I want to go back to this figure. We're not isolated from the rest of the world. So we're not just warming locally. Things that happen in Greenland, things that happen in the Arctic, things that happen in the tropics affect us. We're connected to the rest of the world. What we do here and how we react is going to be based on how the broader globe is changing. So, key points. What is the cold pool? It's a dynamic ocean feature. It changes a lot, but generally it's 10 degrees C, less than 10 degrees C, and 34 PSU. Where it can be found, we found as shallow as 10 meters below the ocean surface. You can't see with satellites, so you have to go out and touch it to see it. In summer and fall, mid to outer shelf between Cape Hatteras and Cape Cod. How does it form? Remnant winter water, and then cold water transported southward through winter and spring. And then it has this rapid summer heating that happens throughout the summer. How's it broken down? Gradually, it warms from tides, a little bit of winds, but then really storms are what breaks it down. They're the big thing that hits it. And then is it changing? I just went over that. So with that, I'm going to hold questions till after Scott finishes. So I'm going to pass it on to him to look at some of the details of the coastal ocean.
Okay. Thank you, Travis. So the first slide is going to remind everybody why we're here. This is the Tuckerton field station that's just down the street here. It's been an incubator for ocean reservists since 1989. This was the vision of Fred Grassley, our founder. He was a visionary ocean explorer. He was the one that had this concept of telepresence and the importance of that, the importance of bringing the ocean into our classrooms, bringing the ocean into our communities. If there's issues in the city, people have walked the cities, they understand cities, you can talk to them. There's an issue in a forest, people have been in forests. There's an issue in the ocean. Very few people are lucky enough to work at sea. Many of them are in this room. But most of the communities, most of the people in the community are not. And so this concept of telepresence, how do we go out and touch that ocean, touch that cold pool that Travis was talking about, and bring it back to study and to benefit society. So that was Fred's vision. This was our incubator. We started here, we built up there. Many of you have been with us for all these years, building these observatories. And so we scroll down to where we are today, and this is our control center for that ocean observatory, one of the most advanced ocean observatories on the planet. We are the operations center for MARACUS. Gerhard will talk more about MARACUS later. We have satellites that map the sea surface temperatures from space. We have the HF radar network that then map the surface currents, and we'll use that information. We have the gliders that go below the surface and go out and touch things like that cold pool that we can't see from space. They're all simulated as ocean models. John is here for the ROMS model. We have Joe here for the WRF model, and the glider lab, and all those things are prepared to go to sea. So those are the facilities that we're using. I'm going to show you a couple of pictures that have come up that we produced over time in this observatory that relate to what Travis was saying. First thing Travis talked about was this thermal structure of the cold pool and how it forms over the year. This is our endurance line. It's right off of Tuckerton where we started doing these cross-shell transects year after year after year. And here's a summary of what happens in the winter. It's all cold, top and bottom. In the summertime, the sun beats down on it and warms up the top and causes this intense stratification with this cold pool below the surface. This is some of the strongest stratification in the world. But there's more than a thermal signal. So let's remember there's also a salinity signal to this. And that's shown right here. I like this summer of 2006 example because of what was called the Albany Puddle. There was a large rain in upstate New York. It all came down the Hudson. It came down the Hudson, went out onto the shelf, and spread over the whole area. And so, very fresh water that year. Fresher than we've seen in many of the other years. On top of this, to enhance that stratification. Okay, so there's also this freshwater inputs that are changing, that are increasing the stratification. This is the key piece of what we're looking at gliders going below the surface. The other side of this is offshore. Offshore, the water is very salty. So there's these saltwater intrusions that come in, and you see them coming in here. Those saltwater intrusions, like you see right here, this high salinity, these plots are salinity, fresh water, salty water. These come in from offshore, and they go onto our shelf. And if a storm comes or something like that, it mixes it down. Most of those intrusions are in the bottom to bring that salty water into the bottom layer. So not only do we have the temperature, the thermal structure, the heat from the sun from above, the cold water from the north coming in to enhance that thermal side, we have the salinity side enhancing the stratification. Fresh water from the rivers coming in and spreading over the surface, salt water from offshore coming in to the bottom and enhancing the stratification. I now want to talk just about 3 points of the cold pool and its interaction with the atmosphere. Okay, so that's the part that we're going to talk about here. We're going to talk about 3 different processes. We're going to talk about upwelling, downwelling, and mixing. And how upwelling of the cold pool, downwelling of the cold pool, and mixing of the cold pool impacts the atmosphere. So first is upwelling. And this occurs when we have this thing called the Bermuda High. This high pressure system off of Bermuda, and the winds are coming up here. These are those hot, hazy, humid days that we have in the summer, where that Bermuda High locks in, and you get those slow winds from the southwest for days and days and days. Right? It gets really hot here at the beach, and people turn on their air conditioners and they use a lot of power. And so when the wind is coming from the southwest like this, we have a situation where the wind is blowing from the southwest, that surface water is pushed to the right. We have that turning earth thing going on here, right? So the water is pushed offshore. The surface water goes offshore, and the beach doesn't get dry. So cold water has to come up from the bottom. And that's this process called upwelling. This upwelled water has nutrients in it, causes the surface blooms. We'll hear more about the surface blooms and things like that. Those biological pieces from race. And then, it all relaxes, the water comes back, the blooms decay below the surface, we have the low dissolved oxygen that the Department of Environmental Protection is so concerned about. And so this is what happens here, is that we get those winds from the southwest, they pop up the cold water, and that comes to the surface. It kind of spoils the beach days for those people, right? They just, bought their cabins for the week, and the water's cold. What does it look like from a satellite image? So this is from one of the satellite images that we get, those satellite receivers that we have. And there's cold water at the beach and warm water offshore. Cold water at the beach, warm water offshore. This is one of the wind development areas in the New Jersey area. And we see that these upwelling areas impact that area, that region. So the water appears very cold at the beach on these days when this is happening. That impacts something called the sea breeze. Okay, the sea breeze is very important here in New Jersey. The sea breeze is caused by the land heating up and the water being cold. So the land heating up in the daytime, the air rises, it starts to circulate itself, the cold air comes in. You can feel that sea breeze front as it goes by you. You're driving down from New Brunswick down here to Tuckerton, and suddenly you cross that sea breeze front and you have to roll up the windows and put on a jacket. It gets so cold as this is coming in. And so we care about this sea breeze, and this depends on the land-sea temperature difference. And we just saw that the upwelling changes that land-sea temperature difference. So it's going to change the sea breeze. This is something that Rich Dunk has been researching for years on this. And so here's just some examples of what that looks like and why that's important. This is the power use. 3 curves on here. Black is the power load that we have here in New Jersey. And you see that there's a high use of power in the winter, heating and all that, and there's high use of power in the summertime. Okay, that's air conditioning, things like that. So we have to worry about this high use in the summer. Sea breezes occur, there's a couple of peaks. One's here in the spring, and one's here in the summer, where you have these sea breeze events going on. The third line on this graph is blue. This is when the upwelling events peak. The upwelling events peak at the same time in that summertime when we have that peak in energy use and the peak in sea breeze events. So this interaction between that cold ocean that's generated by the cold pool and the sea breeze and the power use is something that's very critical, not only in New Jersey, but across the Mid-Atlantic Bight. And so just to look at what the ocean land-sea difference looks like for a couple of these situations, let's first look at the spring. You can see all that in the back. This is a picture of the whole Mid-Atlantic Bight. The land is very warm, and the ocean is very cold. Very cold everywhere. This is a very easy sea breeze to model. You have one temperature for all the ocean. It's there, it doesn't really matter what scale you're modeling this at. You have a very simple sea breeze in that case, in these April cases, when the power use is low. So if we look at the same situation in the summertime, here's the sea breezes. Here's the sea surface temperature in the summertime during these upwelling events. Cold water here with a very important shape, the warm water near the coast, and a very complicated, highly variable situation with the sea surface temperature. Now you have to include this land-sea temperature difference with a highly variable ocean in your calculations of what the sea breeze is. That's hard. This requires the high-resolution models that people like Joe run to model this correctly. So this is the important piece that we care about a lot. What do these upwelling events look like due to the cold pool coming to the surface? How does that impact the sea breeze in this important time of the year? Okay, so that's the first process we're looking at, upwelling. Now we want to look at the downwelling and mixing. And that comes from storms. Oh, one more slide. This is just the difference between what that cold ocean with the upwelling of the cold pool versus the warm ocean without the upwelling of the cold pool. And these are the winds that result. And there are areas of high winds and areas of low winds, and you can see that they're different. And so some of these differences are very important, especially when we want to look at offshore wind. So it's important to keep this influence in the models as we move forward. So there's this important influence of the ocean on the atmosphere. Now we'll look at the downwelling and the mixing processes. And for that, we're going to look at two storms. Hurricane Irene, which came up the coast along this way through our observatory with this HF radar, and resulted in a lot of cross-shore winds. The other hurricane we're going to look at is Sandy, which came in from offshore, and as a result had a longshore winds. So the longshore winds is the example of downwelling, and the cross-shore winds is the example of mixing. I'm going to show you what those two impacts were on the cold pool and how they fed back on the atmosphere. First is the Irene case. When we look at the sea surface temperature before and after Irene. And so here's the warm sea surface temperature of the surface before the hurricane. The hurricane comes over, there's a lot of mixing, and there's a big temperature change afterwards. It's much cooler over the whole Mid-Atlantic Bight. And if you look at that temperature change, it's about 11 degrees centigrade. 5, 6, 7, 11 is the maximum. 1 degree centigrade temperature change has a big impact on hurricane intensity. We're trying to get it accurate, to accurately predict the intensity of hurricanes. We have 10 degrees centigrade, an order of magnitude more temperature change from the sea surface temperature during Irene. When did it happen? Satellites tell us before and after. The gliders were out there during this event. The gliders had it warm at the top and cold at the bottom before. Here's the depth, and here is time. As time passes, and here's the eye coming over. As the time passes, there's cooling, there's mixing of that surface layer, and that cooling occurs before the eye goes over. And so that means the eye of the hurricane is going over cold water. What happens when an eye of a hurricane goes over cold water? It diminishes. The sucks the energy out of it. Instead of the heat flux being up into the hurricane, which intensifies the hurricane, the heat flux is down. It's into the ocean. The hurricane's warming that ocean and de-intensifying. And so with Hurricane Irene, when it was coming ashore, people remember what the governor's evacuation plan was. He got on the radio and he told us all to get the hell off the beach. Right? And nothing happened. And so nobody believed the forecast anymore, and from Irene. And so we said that that's because of this cooling that goes on. And why does that happen? Because there's the cooling that's going on. Here's that HF radar. Here's the center of the storm. Here's those currents coming on shore. Those currents are blowing that warm water onshore. It's piling up. The water shoots out the bottom. It causes the shear between the two layers. That causes mixing, and that cools that surface layer. And it cools it rapidly, and it cools it faster than we ever thought. Because back in the 12 hours that storm went by, and it de-intensifies the storm. None of these processes are in our forecast models for hurricanes. That's what we're doing. We put that in there right now. That's our meeting on Friday. And the next step is putting those processes in our hurricane models. So we've identified these new processes, and it's all because of the cold pool. The cold pool is there. It gets mixed by the hurricane. It cools the ocean. What's the impact on the atmosphere? So there's 4 different pieces here. Here's the warm sea surface temperature and the cold sea surface temperature. So this is without the cold pool. If no cold pool is considered, like our present hurricane forecast models, and this is if the cold pool is there. Here's the heat flux. The heat flux is the heat engine for the hurricane. With the warm ocean, the heat flux is in, the hurricane intensifies. That's the forecast that went out. That's when the governor said, get the hell off the beach. The ocean cooled, the heat flux changed sign and went the other way. It de-intensified the storm. If you look at the impact on the wind speed, a big Cat 1 or 2 storm hitting us, here, a tropical storm hitting us. 10 knot reduction, that's what we saw. If we look at the storm surge, almost 2 meters of storm surge in New York, much less observed. Bringing that back down into where it should be. And also, if we look at the warm SST, the rainfall versus the cold SST, the reduced rainfall back to what was observed. So by including the cold pool in our forecast for Hurricane Irene, we got the heat fluxes right, we got the wind speed right, we got the storm surge right, and we got the rainfall right. We made a much better forecast of what that hurricane could do. And so this is what we want to do for the hurricanes in the future. So that's the mixing process. One more process. Hurricane Sandy. This one, the year after Irene, the hurricane's coming up to the coast. The governor says, get the hell off the beach. Nobody believed, right? He just told us last year to get the hell off the beach and nothing happened. It took days to convince people that Sandy was going to be just as bad or worse. And why was that? Again, it's the cold pool. This is Travis putting the glider out. We had 7 days warning that Sandy was going to come. We had plenty of time to prepare, but we weren't sure of the intensity. And here comes Sandy with its alongshore winds. It's coming in this way, and the alongshore winds in this area. Just like the alongshore winds from the south cause upwind, the alongshore winds from these storms cause downwind. This cold water that was here, our cold pool, that's our protection, it's our fire extinguisher for the hurricanes. Sandy pushed it all offshore. And we saw that with the gliders. All that was left was warm water when Sandy came by. And with just warm water, what does it do to hurricanes? It intensifies. And so we're sitting here knowing that Sandy's going to come in hot, fast, and there's nothing we can do. So that's what we want to change. And this is just to show that we're very good at predicting that down. So this is our conclusion on the hurricanes and why we care so much about this cold pool and having that in our hurricane forecast. We have this essential ocean features, the seasonally warm surface layer, and the persistent cold pool at the bottom. 2 key processes for these different storms. One is the head of eye mixing and cooling that we saw with the Irene class storms. Most of the storms that come by our area like that. We also saw the head of eye down. And then, what are these feedbacks on the atmosphere? Irene, that mixing and cooling causes a rapid de-intensification of the storm. The downwelling of the cold pool causes an intensification of storms like Sandy. So the cold pool was critical for all these things. The cold pool causes the upwelling, which impacts the sea breeze on a day-to-day basis. And the cold pool, whether it's downwelling or mixing, impacts the storm. One intensifying, one de-intensifying. That's why we care so much about the cold pool.
Any questions for Scott or Travis? They're also going to be here all day. But as we transition to the next talk, questions?
Scott, question, Sandy. I mean, I have a lot of questions. Just really great stuff. And I can understand what happened with that reef in terms of seeing that cold water leading to no intensification of the storm. But with Sandy, it was different processes. Two storms, totally different characters.
Yes.
Irene is coming in late August when you have that real intense cold pull is in place. Sandy's coming in late October when you're seeing all the climatology, the dissipation of that cold pull. But there's a totally different track to these two storms process. Sandy never intensified as it approached the shore. The wind field expanded and the pressure dropped because of that, because the huge wind field is what really made that storm meet and its track. And so it went through this extra tropical transition. It's not going into the hurricane. So I wouldn't say that you had this intensification of Sandy. The cold would really play any particular role. I mean, I have to go through literature, obviously. In terms of the Sandy damage, I mean, it's just a different storm. But that storm really was more a creature of that transition, that huge expansion of the wind field. I don't know if that cold would really have played a role in its intention at that point as it's going through that transition.
So all those things that you said are true. There's all these things that are going on with Sandy. But you can also look at the, just as it's approaching landfall, and just those final hours before landfall where there's that slight intensification that we were able to get with the warp model that we see, which is probably the best forecast of Sandy completely. And usually what we're expecting to have go on in that case, in these hurricane cases, are the cold pools and mixing that helps de-intensify the storm. In this case, there's many different processes all going on at once. The impact of the cold pool being downwell, leaving only warm water, and that warm water is then going to be warmer than the air. And so that's going to lead, that process is going to contribute towards intensification. There are many other processes all contributing and balancing each other.
But the thing is that the track of Sandy, there's two things. Number one, the highest winds were well north of the central, 200 miles north of the central courses. And the other thing is that the track across that warm water it's minimal when you think about it, because it's coming in from east to west, whereas Irene, which is a great case, which you showed, has got that much longer south-north track over that cold, which certainly won't definitely tell them that would certainly lead to a less.
The track is critical because it makes longshore versus cross-shore winds, and that's the key. When we have hurricanes like Sandy, a Sandy-class hurricane that produces longshore winds, that causes the cold pool to down and get out of there. So it just leaves warm water. So there's no protection from the cold pool. Irene is cross-shore winds. There's 10 or 11 storms that in our history that have done those cross-shore winds. Those winds cause mixing.
Yeah. And
so that's the different processes that are impacting the cold pool. One leaves a cold pool there that can cool the top and act to de-intensify. With the Sandy-type storms, where it's a longshore wind, or any northeasters, where you have those longshore winds, that moves the cold
offshore.
Is
there's great cases of that. You can go back to the 1970s when Hurricane Bell. Hurricane Bell was a category 2, almost category 3 storm hit Long Island. Just hit that cold bowl. Back then, obviously, early. And it just lost more strength pretty rapidly before it came across Long Island. So.
Yep. Okay. Great. Good stuff.
One more. Hi there, Peter Hughes. Where are you guys when these storms take place?
We're usually up in New Brunswick.
Yeah. Well, you're at the lab.
Yeah, but the gliders go out.
Well, I know that the gliders are out, but I'm just wondering, when these events take place, is it like, all right, let's go, let's get in the lab, let's hunker down, and let's see what's going on?
Well, the observatory, so I was actually sitting in Manhattan on my laptop watching the data from the glider and Sandy come in. And so the observatory's out there, and so we're communicating, we're home, we're batting down our own patches, but we're all looking at the same data up until the power goes out, basically.
And then who informs the governor? Because the governor, just before this storm, it was up around Delaware Bay, and kind of went a little bit east.
The National Hurricane Center.
Yeah. National Hurricane Center.
That's the official word. Yep. So everything that we do has to flow into the National Hurricane Center so that they can act on it and produce the official forecast. We can't produce a forecast for a hurricane because then it could be different. You can't have two different.
Well, I understand. So your data feeds directly.
Yeah. Everything we do is goes through the National Weather Service, through the Hurricane Center, and where do we get? Like Josh and I spent Floyd in this room. We spent different hurricanes, different places, but yeah, wherever you got to go to get that stuff in the water before the hurricane, which money you have, and then now it's wash it off.
The only other thing I'd like to add is that about 10 minutes, 15 minutes into Travis's portion of the presentation, I was like, boy, I hope somebody's filming this because I would really want to refer back to your presentations because it's fascinating. For somebody that has worked on the water in the past, this is new information for a lot of us. Well, some of us who are ignorant of this. It's new information to me, and it's fascinating. And the hour that you took explaining this to us is an hour that I would like to share with others. And was kind of wishing that.
I saw you show with the track of Sandy, and I'm just wondering if that sharp turn was a normal thing or an abnormal thing. There was a lot of the press about the different models they were showing, and it just kind of zeroed in.
That was the large scale interactions with the larger scale steering currents. So there was the high pressure up over the Atlantic, and then there was the low that was coming down from Chicago, and the low with the Sandy. The two merged, and they were blocked by the high pressure ridge, and it caused that turn. And 7 days before, we're starting to get warnings that was a possibility. We got it from the European source. And so that's what we were reacting to. That's, okay, we better get our stuff in the water, because this could be a bad one if this really comes true. And it's turned out to be.
So there's a study that under past climate scenarios, under just past data, that it had approximately a storm like Sandy has like a 700 or 400 year return period. There's a lot of uncertainty on that, a couple hundred years of uncertainty on that, and that's under past scenarios. So that's doesn't mean it won't happen.
I'm going to take a look at hurricane history.
Okay, yeah, well, yeah. And so, that being said, there are very frequent nor'easters that don't necessarily take that track, that have similar winds along shelf that can drive the cold pool, but can also drive surge, storm surge, and things like that, and inundation. So, I think it was considered relatively rare, but that's not necessarily, doesn't mean it's never going to happen.